Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Why does a Stradivarius violin sound better than anything made today? For centuries, musicians and scientists have puzzled over this question, attributing the magic to everything from secret varnishes to the master's own prayers. However, recent breakthroughs in geochemistry and dendrochronology suggest that the secret isn't just in the hands of the luthier, but in the very atoms of the wood itself. Atoms shaped by a unique period in Earth's history known as the Little Ice Age. Between roughly 1645 and 1715, the Northern Hemisphere experienced a period of extreme cooling called the Maunder Minimum. During this time, solar activity plummeted, and winters became brutally long and harsh. It was exactly during this window that Antonio Stradivari was active in Cremona, Italy. The spruce wood he used for his instruments, sourced from the forests of the southern Italian Alps, grew under these extraordinary climatic conditions. When trees grow in a stable, warm climate, they produce wood with wide, varying growth rings and significant differences in density between the early wood produced in spring and the latwood of summer. But the Little Ice Age changed the rules of biology. Because the growing seasons were so short and the temperatures so consistently low, the trees grew incredibly slowly. This resulted in growth rings that were extremely narrow and, most importantly, remarkably uniform. Modern CT scans and isotopic analysis show that Stradivarius wood has a density profile unlike any wood harvested in the 20th or 21st centuries. In a standard modern violin, there is a large mechanical gap between the soft early wood and the hard latwood, which can cause sound waves to scatter or lose energy. In a Stradivarius, the transition is seamless. This uniformity allows the wood to vibrate as a single, cohesive unit, producing a brilliance and a carrying power that is often described as silky or vocal. But the mystery goes deeper than just density. Isotopic analysis, which looks at the specific ratios of oxygen and carbon atoms within the wood's cellulose, has revealed another layer of the secret. The specific oxygen-18 isotopes found in these instruments act as a chemical fingerprint of the alpine snowmelt that nourished the trees 3 centuries ago. Furthermore, research led by Dr. Joseph Stradivari suggests that the wood underwent a chemical transformation before it ever reached Stradivari's workshop. To prevent rot and insect infestation, loggers often soaked the timber in local rivers or treated it with a cocktail of minerals including borax, zinc, copper, and even alum. These minerals didn't just preserve the wood, they created a process of mineralization at the molecular level. Over decades and centuries, these minerals fused with the wood's lignin and cellulose, essentially turning the organic material into a semi-fossilized state. This process increased the wood's stiffness while reducing its weight, a combination that is the holy grail for acoustic engineering. High stiffness means the wood can vibrate at higher frequencies without warping, while low weight means it requires very little energy from the bow to set the air inside the violin in motion. This is why a Stradivarius can whisper in a way that is heard at the back of a massive concert hall. Today, luthiers are attempting to replicate this using everything from high-tech fungal treatments to artificial weathering in climate-controlled chambers. Some use bioengineered fungi to eat away the cell walls of modern wood to mimic the low density of the Little Ice Age spruce. While these modern recreations are impressive, they lack the 300 years of vibrational seasoning that occurs as an instrument is played. Every time a violinist bows a string, the microscopic structure of the wood is subtly rearranged by the sound waves themselves. In a sense, the instrument learns how to vibrate better over time. The Stradivarius is therefore a perfect intersection of celestial events, a dip in solar activity, and human genius. It is a time capsule of 17th-century chemistry, a physical record of a colder world, and a reminder that sometimes, the most beautiful things in art are the result of the harshest conditions in nature. We may never be able to perfectly recreate the sound of a Stradivarius, simply because we no longer live in the world that created the wood. As our climate warms, the trees grow faster and more inconsistently, making the isotopic signature of the golden period a relic of the past. For more incredible facts like this, don't forget to subscribe and turn on notifications.